Okay, let's go ahead and continue with how amazing our limit laws are for us. There's a couple of really big example groups. One is polynomials. So, in case you forgot, what do polynomials look like? They look like powers of x added and subtracted together, and they can have any kind of constants they want in front of them, multiplying them. So really what a polynomial is imagine that you have all the real numbers in the world, and you have x's, and you are only allowed to multiply them together and add them together. And so what you don't get is anything divided by x or any square roots of x, but you do get every power of x you'd ever want out, and every real number you'd ever want out, multiplying all these things and adding them together. So polynomials in general look like this. And what our limit laws tell us is that for any polynomial in the world, you can just plug in. So this is just 7 times 5 to the 6 minus 4 times 5 to the 5 plus square root of 2x cubed plus pi, sorry, not x cubed, 5 cubed plus pi times 5 minus a third. I don't know what that number is any simpler. I think that's fine. That's a beautiful number. Leave it like that. For any kind of a long problem, just leave it out. You're going to do a lot of simplification in algebra in this class. This is pretty great. So polynomials, we're allowed to just plug in because of our limit laws. Just to break that down a little bit, what is our limit law really telling us? It's saying, hey, I can write this first term as 7 times the limit as x goes to 5 of x all to the 6th. And I can go ahead and subtract my next term and say, actually, let's pull out this 4 and let's take the limit as x goes to 5 of x all to the 5th. Plus, and I can keep pulling these things out and doing them separately. Well, what does it mean to keep doing each term separately and then plugging into each term? It's the same thing as plugging into the whole darn polynomial. Okay, so polynomials are amazing. If I want to take the limit, just plug in the value you have down here. The property that we're getting out of this is that polynomials are continuous. Continuous just means we are allowed to plug in for limits. All right, here is another big class of functions called rational functions. So a rational function is just a polynomial divided by a polynomial. And for polynomials as well, for rational functions as well, we are allowed to just plug in. How amazing is this? So 5 times 5 squared minus 5 plus 1 over 5 cubed plus 7. Okay, I don't know what that is. I don't think I want to bother simplifying that. That looks pretty darn good to me. Why can I do this? Well, I'm allowed to plug into the polynomial on top, and I'm allowed to plug into the polynomial on bottom, and then I'm allowed to divide those two polynomials because I can divide two functions. Okay, so this works. I can always plug in to a polynomial divided by a polynomial, also known as a rational function. I can always plug in if the denominator, okay, quick quiz, what's the one restriction I need for that denominator? It's a common theme. So if the denominator is not 0, if that denominator is 0, I'm not allowed to just plug in like this. And luckily for you, it sort of warns you on its own, because the answer you would get out, the number you'd get out would have a 0 in the denominator, and you should immediately say, oh shoot, that's not a number, that's not defined, something went wrong. So rational functions are also super nice. There is another way of saying this. We are going to say that they are continuous. In other words, you can plug in on their domain. So if there was a 0 in the denominator, we would not be on the domain of that function. So two great classes of functions. We're going to get several more in the future where our limit laws or some other rule lets us know you can just plug in. So what about when things go wrong? Or rather, what could still go wrong? Okay, so there's a few things that could still go wrong in this case. We could divide by 0. We definitely don't ever want to divide by 0. That's a big one. So, for instance, the limit as x goes to 0 of 1 over x. Okay, no limit law is going to save us. That is technically a rational function. 1 is a polynomial, so is x, but I can't use my limit laws there. There are a couple other things that can also go wrong. So we could be on the we could have other domain issues. This really is pretty similar to dividing by 0. So for instance, the natural log of x, if I wanted the limit as x goes to 0 from the right, the natural log of x, 0 is not in the domain of natural log of x. In general, actually, we're going to have this other issue, which is we haven't even talked about natural logs yet, or sines or cosines. So we will get there on some of these. The bigger issue is going to be dividing by 0. There's another big one, piecewise defined functions. What on earth do I do with something like, say, f of x is equal to x squared if x is less than 0, and it's equal to, say, cosine of x if x is greater than 0. So we are not going to worry about this middle one very much right now. I mean, it's going to naturally come up when we divide by 0 because that is a domain issue. But we're going to take a minute and focus on what do we often do with dividing by 0 and what can we do with piecewise functions. Okay, so 2 nice groups so far, polynomials and rationals. We love those. A couple areas where we still have to do some work. Let's take a look at that work. Dividing by 0, we got this. If we have a dividing by 0 problem, especially if it looks kind of nice, like a rational function, or there's just a division happening, all it's really telling us is clean it up. Just simplify like crazy, do some work, expand it out, see if you can get something to cancel. So this is going to be very familiar to us. Let's go ahead and just expand this out. In fact, I believe this was a warm-up problem, so I'll work through it fairly quickly here. If I wanted to rewrite this, I'm still allowed to do all the algebra I want in the world. So limit as h goes to 0 of 2 plus h squared. Oops, but rather than 2 plus h squared, we'll just expand this out and say this is going to be h squared plus 2h plus 4. Okay. Do work on your squaring skills. It's going to come up a bunch. It might take you a little longer than me, but we do want to get that as fast as possible. And then we're going to subtract this 4. Great. Notice now those 4's cancel. That's a good sign. And I want to cancel these h's. I'm going to cancel them nice and slow because people often still make mistakes here. What does it mean to cancel something in a fraction? It means that you can factor it out from the top and the bottom. Okay, so I can factor out an h from the top, and I can, kind of silly, factor it out from the bottom. H times the entire top, h times the entire bottom. Once I do that, then I'm allowed to say, oh yeah, it's times h on top divided by h. Those are going to cancel out. What am I left with? H plus 2 over 1. That is now a rational function where the denominator is not 0. And so my limit law tells me, hey, the denominator is not 0. I can just plug in 0 plus 2. This thing is going to go to a 2. This thing is going to go to a 1. I just get 2 over 1, also known as 2. Moral of the story, if you're dividing by 0, good chance what you have to do is expand like crazy and try to get things to cancel. Okay. Now, as with everything in math, there are a few tricks of the trade, like what to do if I have a square root in there. Okay, hopefully you did the warm-up. I don't want that square root in there, at least not right now. The problem, I would be able to plug in. I should check. If I try to plug a 0 in, I get looks like square root of 16 is a 4 minus 4 is a 0 on top, and I get a 0 squared is a 0 on bottom. 0 over 0 is exactly what we would have gotten on this top one if we plugged in, and that is telling you there's a good chance that you can cancel something out, right? If it's a 0 on bottom and a number like 5 on top, it's probably an asymptote, right? But 0 over 0 says maybe I can cancel something out. That's your big, hey, let's get some work done. And the way I'm going to deal with this square root is with this neat trick of multiplying by the conjugate. So make sure that you know what the conjugate is. In this case, it just means I change that minus to a plus. And I've got to do it on top and bottom. Algebra tells me if I multiply the top and the bottom by the same thing and they are not 0, then I should get something equal out. So I'm allowed to do it. Okay, I'm going to do this a little quick here. Practice at home, FOIL this top thing out, make sure you get what I'm about to get, but I should get t squared plus 16, because I'm going to end up squaring that square root. My middle terms when I FOIL are going to cancel, because that's why I picked the conjugate, so they would. And then I get a minus 16 here. All over t squared times big old parentheses square root t squared plus 16 plus 4. Okay. Whew. All right. This looks kind of nasty the first time you do it, and then it starts going pretty darn fast because it goes the same each time. These 16s cancel out. That's nice. I have a t squared on top and a t squared on bottom. So this, when this becomes t squared times 1, I can cancel those out. Oh man, sorry for being a bad role model for keeping your work clean, but I'm running out of room here. What am I left with on top? Just a 1. What am I left with on bottom? This big square root thing. Notice the bottom if I plug in a 0 isn't 0 anymore. So I'm allowed to just plug in that 0. The bottom looks like it's going to go to square root of 16 is 4 plus 4 is 8. This whole thing is going to 1 over 8. Nice. Okay. Neat trick, the conjugate, notice, is not going to 0. But if I multiply by the conjugate, then I can get rid of that square root on top, which was in our way. All right, so point being, if you find yourself in a 0 over 0 case, chances are you need to expand out and try to cancel things. All right, next up, piecewise functions. I think I'm going to save this for the next video.